Welcome back to another processing video. This time I'm actually going to start with a kind of scientific explanation of things. So let's begin in paint. And so kind of today, actually it was probably 5 minutes ago, my mom was cooking in the kitchen and there was a lot of smoke from the oil. So when you cook, the oil evaporates from the pan. Let's say that's the pan, right? And there's oil in it, and it goes up in smoke. And basically, that smoke is not healthy to breathe in. So generally, there's a vent up top to collect the smoke. And so some of the smoke, of course, doesn't go into the vent. The vent kind of pushes the smoke outside of the house, right? Some of it does not actually go in the vent, though. It spreads around in the room. So let's say that's the room. The smoke will kind of fill up the whole room when it gets kind of hot enough, basically kind of worsening the air. So the reason why this happens more, it actually doesn't really happen in the summer, because I haven't really thought of this question, and when I thought of the question, it was just now, and it's actually really cold outside. Let me check the temperature. So it's 4 Celsius, give or take. Yeah. So it's 4 degrees Celsius, and all the smoke is trapped inside. And why is that? Well, inside it's really hot, and in red, and outside it's really cold. So what do I mean when I say that? I mean the air is hot and the air is cold, and the process of mixing together hot and cold air, generally the cold air goes into the hot air. That is the principle. And why does that happen? Well, cold air is more dense than hot air. So hot air kind of, the molecules jiggle around more. You can think of it that way. So they have more kinetic energy. They move at a higher speed. But the speed is not important. What's important is the result of having a higher speed. Having a higher speed means, it gets more spread out, the particles. And that means it's less dense. So the denser particles, that are more packed together closely, will go into the regions where it is more spread out. Yeah. And I'm going to write a processing program to demonstrate that. So let's first create our void setup and void draw. Alright, and then I'm thinking of having just a lot of balls inside of an array list. So the balls will represent the molecules. Let's call this molecules. Molecule. We can call this molecules. Actually, I think this is supposed to be capitalized. I'm not sure. I'll keep it lowercase. Molecules equals new array list molecule. We can set the size to maybe 500. I don't think we need that many to demonstrate the point. And we can also learn about subclassing here. Alright, so let's make a class called molecule, of course. And we need a constructor here, so molecule actually needs this. Alright, so the inputs, I think I'm going to set it to random. I don't think we need inputs. Alright, so we need some values here. So I should probably use doubles. Yeah. So generally in Java, people use double, not float, because double is more precise than float. although people do think in terms of floats generally, like in intro classes. Alright. Actually, we don't really need that much precision, it's like whatever. Alright, so float. I'm just gonna use p vectors actually. P vector position, p vector velocity. There's no acceleration. Alright. For the collisions, I'm not gonna do like conservation of momentum. That would be way too much work. Alright. So position equals new p vector, and inside of here I want to put random. Let me set the width and the height. So background can be white, and then size will be, let's do 800 by 800, and then height. Alright, so that's our position. Velocity will equal, this one can be, wait, what's it called? P vector dot random 2D. Yeah, so random 2D makes a random two-dimensional vector that is having a magnitude of 1 but a random direction. Okay, we're going to need some movement here, so for move, we're going to do pos.add velocity. I think that changes position. And for the other stuff, we can do it outside. Or actually, let's see. Is this possible? This will be right. I think I have to do the rest outside. Yeah. Okay, so collisions will be handled outside of the molecule class there. But first, let's add like 500 things to our list. So molecules that I need to do a for loop for I wonder if there's going to be the problem of not having a big enough list. I think that was a problem in C. I don't know if it's a problem in Java. Whatever though. Molecules. I think I can do this. Wait, if I do .get, does it actually change the value? Okay, I don't think that works. Yeah. I'll just do this. Molecules.append. It's not append, is it? Molecules. I think it is actually. Oh, it's not real. What the heck? I actually forgot what it's called. Let me see, I'll just look it up. How to add. This is the problem with not practicing your syntax, by the way. How to add element to array list, Java. Oh, it's .add. And here I'm going to just run the move function and see what happens. So also inside of here, I want to do the collision with the wall. So let's see. If velocity, no, it's actually if position greater than if here I'm going to reverse the velocity. I need times equal -1. And I'll repeat this for y. Wonder if there's a better way to write this. Probably not. Okay. Now I want to display all of them. So I'll just I guess I can use the display function. Void display. So in the display, I'll just draw a circle. I would probably stroke to stroke to be 0. I want it to be black. Stroke width is 1 by default. I think stroke is black by default. I don't know. Wait. I'll just do this to make sure. And then circle takes position in x, so cos.x, cos.y, and it also takes the size. I'll just make it like 5. That's the diameter. Probably do an even number. Okay. Let's do 4 actually. Okay, now in draw, the molecule I want to display, m.display, call that method, m.move of course, and we will be checking for collisions. And we're going to do that in n squared. There's like a fast way to do it, but actually, we'll just do n squared. The other method is kind of annoying. Alright, let's just see, does this work for now? Oh, I didn't do that. Okay, but it's like displaying properly, so that's good. Background. Well, a really nice thing is you can set background 255, but you can also do like a transparency. So like, let's say I did like 50 for the transparency. It leaves a might be between 0 and 1 actually. This is confusing. I wanted to leave a trail. Oh, whatever. Let's not worry about that. Do I have to do it over? Oh, it's not background. You have to do you have to make a rectangle. So rectangle, I don't know the mode. I'll just set it rect mode. I want it to be centered. So here I'll do width over 2, height over 2, width and height. This is very convenient. It's much better than actually any way of drawing the rectangle. Very convenient. Alright, so I want to fill 0 and then 255 and 0.5. Yeah. And then I have to set the fill here now. Okay. Fill 255. This is not working how I thought it would. I think I have to do a bigger number. Yeah, here you can see like they all leave like a little trail. It's because we're drawing on a slightly transparent rectangle over the top of these things. Every single frame. And you can make the trail longer or shorter. And slowly the trails disappear. I think there's an optical illusion that the trails have not disappeared. Yeah, that's pretty interesting. But okay, now we can see all the moving around. Now we're going to check collisions. So, actually, instead of doing this, we're going to just use traditional for loop. For int I equals 0 or less than molecules.length. I think this is it. Is it a function? Whoops. Oh, it's size. Yes. And then an easy way to adjust for using m is you can say m equals molecules dot get I. Oh, you have to say molecule. Okay, and now to check the collisions, we're going to do for int j equals I, j less than molecules dot size, j plus plus, and actually we're going to do I plus 1, and less than molecules dot size minus 1. This way, we only check the same pair once. So it's kind of n squared over 2 time rather than n squared. Although for time complexity you should still say it's n squared. Alright, anyway. To check the collisions, what we're going to do is see if they're on top of each other essentially. So I'll create a distance variable. Dist equals. I'll do the distance squared. Yeah. Right. Can I use distance squared? I don't think it would work out. Yeah, I don't think so. Okay, dist equals this. Although if you used like an approximation of the distance rather than doing the square root function, it would be faster. Because the square root function is really slow. Okay. So I want, let me call M2 molecule equals molecules get j, and then this equals this. I wonder if it takes these? No. Okay, so m dot x, m dot y, m2 dot x, m2 dot y. Wait, what? I'm using dot x though. Why is it giving me this? I can't do m dot x. Oh, m dot pos dot x. Okay, I'm a bit silly. Okay, that's the distance. And if distance is less than, I made it 4 big, so they would be 1 diameter apart, assuming they collided. If distance less than 4, then it means they have collided. So essentially we will now reflect them in whichever direction they were. Actually, wait, I'm pretty sure. So first of all, momentum is conserved, and that's too much calculation. I'll just take the direction that they're both pointing in. Okay, so the vector that points from, I don't have to use this. I can do this. Okay, watch this. P vector 2m2, that is going to be equal to P vector dot sub means subtract, by the way. I'm going to subtract m2 dot position from, I'm going to do the opposite. I'm going to subtract m dot position from m2 dot position. So what this does is I get a vector now. Let me draw this. So let's say this is the first ball, this is m, and this is m2. So these are their centers, and then this vector is the one that we have just created because we've taken the position of the first, or the position of the m2, and we subtracted the position of m1. So the way to do this is you can say that this vector, if you add it to the position of m1, that'll equal the position of m2. And so naturally, you can say that this equals m2 minus m1. That's the idea. Okay, so now, instead of saying this less than 4, we can say 2 underscore m2 dot mag. Okay, mag is a variable, or whatever it is called. If this is less than 4, then we will be moving them, changing their velocities. So m dot velocity times equals -1. Okay. And also m2 dot velocity dot -1. Too lazy to do the actual collision math. Oh wait. Let's see. This would work like generally, maybe not like perfectly, but generally it'll move back in the direction, although I think it should be more like that equals m2 dot set magnitude to 1 times -1. How does this even work? To make a y I don't really know what I want to do. Let's just like, for now, just do dot multiply by -1. Some of them are not moving. Oh, they're stuck in a cycle. Yeah, because they spawn on top of each other, I'm pretty sure. Well, ignoring those, the program works okay. Yeah, okay. So now for the experiment, we can try spawning a lot on the left, and then not as much on the right, to kind of emulate how cold air is dense, and hot air on the right, that will be, what's it called? Not dense. Okay. Maybe on a subclass. Yeah. I mean, the only purpose would be to set the color. So let's just do like color C, and then fill C. Wait, no. Color underscore C. Alright. Or is it C underscore? I don't remember what the convention is. I'm assuming it's gonna be C underscore. Actually, I think it's underscore C. This feels more natural, I don't know why. And then instead of filling 2 I probably fill C. Alright, so for in I equals 0, I less than 500. Let's set the positions too. Underscore position. Cost equals new p vector. Nope. Underscore cost. So let's have 500 on the left, and then not as many on the right. So on the left it's going to be dense, so we're going to do the color blue. So position will be new p vector, random click over 2 to random type, and afterward we will be giving it color, so let's make it color 0, 0, 2.5, and then here, copy paste. Over here we're going to have the red. what happens. Alright, so we can see as time goes on, there's going to be more blue particles. Let me just make them a bit faster. And also the trails, I don't really like the trails being that long. Oops. Alright, so you can see as time goes on, more of the blue goes to the right, just the number of particles in general, and less red particles are able to move left. So this is kind of like how hot air this is kind of like how cold air goes to hot air rather than the other way around. It's also why basically when hot water is on a layer above cold water, there's going to be basically like a lack of like mixing, because the hot water has no reason to go below since it's less dense, and then the cold water doesn't really want to go up because it's denser. So the idea also works in the vertical dimension. Yeah, so disregarding the getting stuck, but also the lack of physical collisions, this kind of demonstrates the principle pretty well. So thank you guys for watching, and see you guys next time.